have is I want you to accomplish the safety quiz in the lab portion and do experiment to both the lab reports and the quiz. I will try to return the graded lab report by tomorrow for the first experiment. Okay, I'm still adjusting now. With regards to the chapter quizzes, so I saw there that the time that you spent for the quiz range from what 6 to 36 minutes. So I think the time given to you is really more than enough. Okay, and I know although the score is not good, but I would say this is just the first time that you did the setup, and I expect everyone to we could say improve. Okay, if you use the material that we have aside from the lecture that we have here, I hope that you just don't depend on the lecture that I'm giving you. Okay, because this might you will not be able to absorb a lot within what 3 hours. That's why I tried to make it a little bit short, because they said after 1.5 hours the brain can only absorb a little too much. Okay, so if you have watched this video that we have regards to chapter 2, the lecture that I have is just the same, because I'm using what we call the same materials. And I want you to prepare for chapter 3, because that's where most of the students' problems comes in. Okay, because that's where calculations started. Okay, and chapter 3 quiz is the longest among all the quizzes that you have so far. I set it around 1 hour and 30 minutes just to prepare you, because those are all what we call calculations, most of them. So to continue the class, we have done with chapter 1, where we have tackled about matter, okay, and measurements. Now in chapter 2, we're going to deal on how this nature of matter, especially the atomic structure, came into being. Okay, so this is some sort of, let's say, a history. But if you're going to look at it, this is, we could say, an evolution on how we know the present stuff in chemistry. So it has here atoms, molecules, and ions. So if you're going to look at this, these are the building blocks of chemistry. You are introduced with the atom, the basic unit that made up the element. Molecules, that's the basic unit that made up the compound. Okay, ions is just the charged particle. So you're going to tackle more about this, how we name them, and how we build them up to have this so-called chemical reaction. So the nature of what we called atom during that time, everything during the Greece has something to do with what we call speculation. So when we're talking about speculation, it's more on philosophical ideas. There's no empirical evidence. Okay? And it took Leucippus, Democritus, and Epicurus several years, okay, to theorize that matter could not be infinitely divisible. And I think the main credit goes here to Democritus. So what Democritus do, establish some sort of a theory that when you divide any matter, there will come a time that it will not be divisible. Okay, so there comes a time that there's a limit that, at this what we call stage, you cannot divide it furthermore. And he coined the term atomos, which is the Greek word for indivisible. But as what we know before, usually it's not who is right, but who is famous. His theory, okay, of this what we call atomos, that matter is indivisible at a certain point in time, was overshadowed by Aristotle. Okay, Aristotle theory is just what? That matter is made up of 4 elements. Okay, and what are these 4 elements? You have the air, you have the fire, you have the earth, and then water. So what Aristotle said that the matters around us is just a combinations of these elements. Maybe you know them more on what? Is that the last airbender? Ang? Yeah? He's what? An airbender? Okay? So anything that is wet is a combination of this wet material. Anything that is what we call the hot is a combination of this. And anything that is made up of earth and fire are the dry material. And water and earth is usually the cold stuff. And unfortunately, because he's more popular than Democritus, his idea was the one that was accepted, although it's not correct. And for ancient times, that was what we call the one that was accepted. And then came what? The introduction of scientific method. Because during that time, this is the chemistry that you know, alchemy. And what's the main purpose of alchemy? Anyone? Why do we have people that we called alchemy during that time? Most likely, they want to convert cheap materials to gold. Okay, that's one purpose. The other purpose is to find, okay, the so-called philosopher's stone, the one that you have in the first Harry Potter book. Now, although alchemy doesn't really do science, the material or equipment that was used in alchemy is the precursor of whatever materials that we have. Okay? And when the scientific method was introduced, science is a little bit new. It just came after the Renaissance period. Okay? So it takes maybe around the 1800, during the time of the French Revolution, around 1780s, 1790s, when a French aristocrat by the name of Antoine Lavoisier, okay, he studied about the nature of this matter, and he found out that if he react, okay, materials, the mass before and after the reactions is the same. Now, before, what they say that if you burn something, you always says that the amount that you have is, we could say, more than the one that you have when you started. But they didn't consider the presence of oxygen that is responsible for the reaction. Okay? So upon careful measurements, he was able to establish that the mass of the reactant is equal to the mass of the product. And that's the concept of this law of conservation of matter. In a chemical reaction, okay, the mass is usually conserved. Nothing is created nor destroyed. So that's the precursor of, we could say, chemistry. And Lavoisier is always credited as the father of chemistry. Although unfortunately his head was separated from him during the French Revolution. Okay, because he's one of the aristocrats. And at the same time, an Englishman by the name of Joseph Proust formulated this so-called law of definite proportion, or in some book, definite composition. So what does this state? Okay, the law of definite proportion states that a given compound always contains exactly the same proportions of element by weight. So irregardless what's the source that we had, okay, all of these pure compounds are made up of the same composition. It all started when he analyzed this copper carbonate. So he always found that there's a 5.3 copper, 1 carbon, and 4 oxygen ratio. in any source of copper carbonate that he can. Okay? Now, these two natural laws that were established during that time is very instrumental to what we know about chemistry at present. And an English school teacher by the name of John Dalton used this natural law for him to develop the so-called atomic theory. So you still remember what theory is? Theory is some sort of much higher uh, explanation compared to hypothesis. Okay. Now the Dalton's atomic theory, that's an explanation of the structure of matter in terms of different combinations of very small particles given on different particulate or given on different postulate. So in some book it's 5, but here we just look on the 4 postulates of Dalton's atomic theory. Okay, and what John Dalton do is he was able to read about the concept formulated by Democritus. So he derived the term atomos. Okay, and he give that term to the indivisible particle that you have in all matter. So the first postulate of John Dalton, all matter is composed of indivisible atoms. So when he talk about atoms, he talk it as extremely small particle of matter that retain its identity during the chemical reaction. Okay? So each atom of a given kind having the same properties. Excuse me. So that each atom, what he had there is he coined that he gave it the name as an element. So element is a type of matter composed of only one kind of atom. Okay, and he adopted the law of definite proportion to come up with the third postulate. What does he says here? A compound is a type of matter composed of atoms of 2 or more elements chemically combined in fixed proportion. So you see how in science they usually look at the previous knowledge and utilize it, okay, to further explain stuff around them or around us. And he also derived the law of conservation of mass for the fourth postulate. A chemical reaction involves the rearrangement of the atoms present in the reacting species to give new chemical combinations present in the substances formed by the reaction. So he just utilized it that what happened during a chemical reaction is just the rearrangement of atoms. So which means there is a conservation of atoms. Okay? They just form new chemical combinations. But whatever presence at the beginning, that's still present till the end. But till after the reaction, the only difference is their identity. But if you're going to look at the atoms that they have the same type of atom. It's just the way that they are arranged that's different. Okay, now the problem with this atomic theory was able to explain some stuff, and it was really accepted during the time. It was able to explain the difference between the element and the compound. Okay, so the only difference is some of the statement here is not already true. As new devices and new instrumentations are found, okay, number 1 is not already true. Why? In our next discussion, we found out that matter is made up of subatomic particles. So when we have subatomic particles, so that means there's still some small particle that you can find within an atom. Okay, and that's the electron, neutron, and proton. And then number two, okay, it's being debunked now due to the presence of the so-called isotopes. So what is isotopes? Isotopes, they made up of the same element but have different mass. Okay, so that's the only thing that's not true anymore. But 3 and 4 is still true. Okay, that's why until now it's still called a theory, because a theory can only stand up to a certain time. Once new evidence comes in, okay, you have to debunk this what we call theory. Now the good thing with John Dalton, he was able to use this concept that he had in the different theory to formulate the so-called law of multifold proportion. So when elements form a series of compound, the ratio of the masses of the second element can always be reduced to whole number. Okay? So what does it mean? When elements form a series of compounds, the ratio of the masses of the second element can always be reduced to a whole number. So for instance, when we have CO, okay? So in the CO, we have what? A carbon and an oxygen. So this is carbon monoxide. Compare it with CO2. So what's the difference that you have there? They have the same number of carbon but different number of oxygen. So you can have the same number or same mass of the carbon, and all you need to do is multiply by the atomic mass of oxygen, that ratio that they have. So since CO2 has 2 more oxygen than CO, so you expect the mass of the oxygen to be twice the mass of the oxygen in CO. Okay, so 32 grams compared to 12 grams. So this has become the basis of law of multiple proportions. Okay. Now in today's, we could say, setup, we could just say that the law of multiple proportion is some sort of just comparing compounds of the same elements, and the only difference is one of the element is a ratio. Okay, so what other example that we can have here? Maybe like this one, H2O2 with H2O, and then maybe we can have NO versus NO2. So as you could see there, one of the element has the same, okay, mass, while the other element is a ratio of in terms of between what we call compounds. Okay, now this is John Dalton's main contribution to what we call the chemistry field. Now, as I have told you earlier, although Dalton postulated that atoms are indivisible particles, experiments conducted around the beginning of what we call 1850s and later show that atoms themselves consist of particles, and these are what we call the subatomic particles. So the first one who did discover about this is, we could say, J.J. Thomson. So what J.J. Thomson did is he conducted a series of experiments that showed that atoms were not indivisible particles. Okay, so he used an apparatus similar to the one that I'm going to show you here, like this one. Okay, and what you call it, that's a cathode ray tube. So he discovered that the particles that made up the cathode ray tube, the cathode rays, are negative and are all part of matter. Okay, so what does it mean? The cathode rays are what? They are the electrons. Okay. So the cathode rays that you have here is what we call a negative charge, and this is the first evidence to disprove Dalton's postulate. Okay, so Thomson concluded that atoms are not indivisible, as what Dalton has postulated. So what did he observe in this cathode rays that we had? So he found out when he put the magnet, okay, some of the cathode rays are either what? Attracted or deflected in the magnet. So if you're going to look at this like this one. So if you have a cathode rays like this, if you put, okay, the cathode rays to the positive end, it is attracted, but if you put the negative end, it is, we could say, repelled. And I think I have a video of this one. So I'll try to share it with you.
To demonstrate a Crookes tube, a cathode ray tube.
Just want to improve the optimized sound.
We need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode. Metal has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream.
Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward.
So that's the depiction of how the electrons are discovered. Okay, so as I told you, the cathode rays, those are just the electrons. They are negative charge. Now in Thomson's what we call the experiment, he allowed him to calculate the ratio of the electron's mass to its charge. Okay, and it took Robert Millikan to calculate the charge of this so-called electron. And he determined it using the device that you have here. Okay, so he determined the charge on various drops of oil and found the smallest increment in charge, that is the charge of the electron. So look at how crude their instrument is during that time. So when Robert Millikan performed his experiment, he put a drop of oil here and he looked at how they behave through this microscope here. So this is the oil drop experiments that he does. So he had some oil, which is spread here, and then he put some charged plate here. So he was able to find the drop of this, what we call the oil. And from that, he was able to determine the charge of the electron. And I also have some animations for that thing.
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value. 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
So I was amazed with how crude their instrument is, and they were able to discover stuff or information like this one. They're able to calculate the charge of this electron using this what we call device. Okay, but the discovery was, we could say, the materials that they have, the instrument that they have, was further enhanced when the concept of radioactivity was known. Now, Marie Curie coined the term radioactivity, and she's a Nobel Prize winner, both in physics and in chemistry. So he discovered what Marie Curie, this is toward the end of the 19th century. It was discovered that certain heavy elements like uranium emit some type of radiation, and Marie Curie coined the term radioactivity for emission, and for the so-called emission that is emitted by uranium. And he discovered two elements, polonium and radium. Okay. During this time, three types of rays were emitted. So you have the beta particle, the gamma particle, and the alpha particle. Now, I'm introducing this to you because the alpha particle that was used here is responsible for us to know the present model of the atom that is very different from the one proposed by Thomson. Okay, so the scientists would use this alpha particle to bombard different types of matter in an attempt to see what was inside. Okay, now during the time, the Thomson model is what we call the plum pudding model. So in a plum pudding model, what Thomson did is just what we call a pudding wherein the electrons are distributed around it, or the negative charge is distributed around it. Okay, so if J.J. Thomson proposed the plum pudding model of the atom, in which each atom consists of electrons embedded in a body of positive charge. So what Ernest Rutherford want to do is he want to prove if Thomson model is really correct. So he used the alpha particle to bombard the atom. Okay, so what Rutherford expected is the alpha particle will just pass through the atom when he bombarded it. But he was surprised with the results that he observed. Okay, so what he did, he asked two of his students during that time, Ernest Marsden and Hans Geiger. So he did an experiment, okay, wherein he used an alpha particle to bombard gold tin foil on it. And what they try to do is they have a microscope to observe flashes where the alpha particles hit screen. So the experiments done in Ernest Rutherford's lab used positively charged alpha particles to bombard very thin gold foil. Okay, gold is one of them, but he also used other metals. Now, what he observed, most alpha particles pass through the foil, but a few were scattered at large angles, sometimes almost straight backwards. So based on these findings, Rutherford proposed that 99.99% of the atom's mass is in the positively charged nucleus. Okay, so if you're going to look at the experiment that he did, so I always use this animation that's available.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil.
Most of the alpha particles pass through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So the result surprised Rutherford, okay? Because he found out based on the experiment that there's a massive subatomic particle that can be found in an atom. So when you look at it, since most of these are what we could got pass through, and only a few of them was what we call the deflected or hit back, okay? We could say that the one that's something that caused the mass or something that's massive can only be found in the center of the atom. That's why he ended up calling this the nuclear model, okay? With the root word, the nucleus. So if you're going to look at the how he explained the experiment that he had is atoms are mostly what? Empty space. Okay. When we say empty space, the one that you have around it are the electrons, but the electrons mass is so small compared to the nucleus, which we have called the positively charged. And he said that the positively charged, that's the one that contributes to the mass. Okay. So he explained the deflection by the alpha particle hitting the nucleus. Okay, so that's the reason why he made this what we call the explanation, because he was surprised. I think even in his diary he said that it's just like I aim a bullet to a tissue paper and the bullet hit me back. Okay, so this change Thomson's model. So this disproves Thomson's model of a plum pudding model. And if you have this nuclear model here, so what does this nuclear model means? If you're going to look at this one here, okay, the atom positive charge is concentrated in the nucleus, okay, because you only see what small number of deflection. And this what we call positively charged, they had opposite charge as the electron as the cathode rays by J.J. Thomson. Okay, and they were able to determine that the mass of the proton is 1840 times the mass of the electron. That's why I told you the nucleus, or during this time, the proton determines the atomic mass, because it's a little bit massive compared to the electron. Okay, so remember, alpha particle that you have there, that's also a proton. So if it hit with something in the middle there, so that means there's a massive subatomic particle that you have here. Okay, so what does the nucleus has? The nucleus during that time was said to contain the proton, and later on they discovered that there's still a neutral particle that is in the nucleus. Okay, now the atomic radius on the other hand is so big, but around it, that's where you found your electrons. And if you're going to look at, let's say, compare the size of the nucleus to the size of the atom. So if you have a Houston Astrodome, okay, the nucleus is a marble on the 50-yard line. So imagine if you can even see the marble if you are in Houston Astrodome, because it only means that the nucleus is so small, but all mass is concentrated on that what we call nucleus. Okay, so if you're going to look at the subatomic particles, these are the information that you get from them. the proton and the neutron, they have the same mass, okay? But the neutron doesn't have any what we call charge, while the electron and the proton, they have the same charge but opposite, okay? So the charge that you have there, -1 for the electron, +1 for the proton, and 0 for the neutron. Now you may ask, how was the nucleus discovered? So you could say, Ernest Rutherford already laid the basis, but they still find that how come the mass, this one, how come the mass that they observed is always 2 times or more than the mass of the proton? So they say there must be something there. And what James Chadwick did in 1932, okay, he also used the alpha particle to bombard the beryllium. He was able to find the neutral charge, and they coined it neutron. It has the same mass as the proton, but it doesn't have any charge. So that's complete, we could say, the subatomic particles. So we just go until here, because right now they found that there's still much more subatomic particle than the electron, the proton, and the neutron. But we're just going to stop in terms of the subatomic particle here. Okay. So if you're going to look at the physical structure of the atoms that we have at present, okay, based on the different experimental observation, we could say that an atom is composed of positively charged nucleus surrounded by negatively charged electrons. So positively charged nucleus contain most of the atom's mass, and it contains what? The neutron and the proton, or the combined term for them is the nucleon. Okay. The mass of the proton is the same as the mass of the neutrons. And then we also have the electrons, which is the negatively charged, but unfortunately its mass is so light. It's 1840 times lighter than the mass of the proton. Okay. Now, knowing that we have these different subatomic particles that we have, let's try to go on this so-called atomic symbol. Okay, so this is where your periodic table will be handy. Now you don't need a periodic table because during your quizzes, you will be provided with the periodic table. And if you answer correctly the question that contains the periodic table, I can assure you, you will not get 0 in your quiz. Okay, so in your periodic table, what do you see? You see 1, 2, or 3 letter notation. And this is what we call the atomic symbol that represents an atom corresponding to a particular element. Okay. So if you're going to look at this, what we call atomic symbol, usually it's the first letter or letters of the element name. But other would come from what? The Latin name, like let's say gold, silver. Okay, they written as AU, AG, hydrogen, H, helium, HE. Okay, so if you're going to look by convention in this atomic symbol, you can write a shorthand notation for this so-called nuclide. So what do you have here? So this is the atomic symbol. I think I have something here. And this is the mass number. And this is your atomic number. Now, atomic number, okay, usually is written what? At the bottom left. Mass number is the superscript at the top left. Now, what information that we have here? So if we're going to look at these nuclides that we have here, the atomic number, that's the number of proton. While the mass number, that's the number of proton plus number of neutron. Okay. Now, what does this mean? If you're given the nuclide, you can determine the number of proton, the number of neutron, and the number of the electron. So number of proton is just this number here. Number of neutron, whatever number you have here, you subtract it with C, and you have the number of neutron. Now, how about the number of electrons? Anyone? Where will I look at it? If you watch the video, where were we going to look at the number of electrons? So usually it's the one here, the charge. And if you don't see the charge, that means what's the charge? Anyone? If the charge is not written, it is assumed to be 0. So if the charge is 0 here, the number of electron is just the same as the number of proton. Okay, so we will have example on this one. So you are asked here, write the nuclide symbol for the atom that has 19 protons and 20 neutrons. How are we going to write this? So I can put an X here, and then C, and then A. That's how it's written here, right? So I put, what is the C equals to? 19, X, and then 19 plus 20, 39. And if I have a periodic table, what is X? So this is what you have. Where will I get the information of K? It's in the periodic table. And we will go on that today also. So you don't have to worry about it. But the thing that you need to know is, if you're given, let's say, the number of protons and neutrons, you should be able to write the so-called nuclide symbol. And I have some items, several items of that in your quiz. Okay. Now, if you look at the periodic table, you will see there, how come the number, or the so-called mass number, or atomic mass, is not a whole number, unlike the number of the proton, or the so-called atomic number. How come the atomic mass is what? Maybe, let's say, for the element hydrogen, it's like this one. For the element chlorine, it's 35.45. What does it mean? Okay. Now, this is where the concept of the isotope comes in. And this concept of isotope destroyed Dalton's second postulate, that an element is just made up of the same kind. But what they observed, isotopes, these are atoms whose nuclei have the same atomic number but different mass numbers. Or in short, same number of protons but different numbers of neutrons. So for example, for chlorine, you can write it either as chlorine 35 or chlorine 37. So another way of writing the stuff is like this one. So what is common between the two chlorines? Anyone? What is common between the two chlorines here? They have the same?
The same element?
No, they're the same element. Specifically, the same what? The same atomic number. Okay. So if I'm not mistaken, is chlorine 17? Now, how did they end up having an atomic mass of 35.45. So it has something to do with the fractional abundance. So what does this mean? That's the fraction sample of atoms that's composed of particular isotope. So if you have a 35.45, which do you think is more abundant? The chlorine 35 or the chlorine 37? Which do you think is more abundant between the two? So if you say 35 and 37, so the average is around 35.45. So that means there's more chlorine 35 compared to chlorine 37 because the atomic mass is closer, okay, to chlorine 35. If what you get is 36, how can you compare the two isotopes? If the atomic mass of the chlorine is 36.00, what can you say about the abundance of chlorine 35 and chlorine 37?
The abundance is the same.
They are?
The same.
They are equal. Okay? So that's how they determine this, what we call atomic mass. But we will have an example on that. But I'm telling you, by just looking at the given atomic mass of the element, you can predict which isotope is present in greater abundance. Okay? So usually they have an instrument known as a mass spectrometer. So they determine the abundancy of these what we call elements. So if you have here neon, which do you think is more abundant? There's a neon 20 and a neon 22. Which is abundant based on the results here? So as you're going to look at here, you have here this one. So we could say neon 20 is greater than neon 22. So there's only a small fraction of neon in the form of neon 22. Compare it to the neon 20. Okay, we will have some calculations on that, but in some aspect, you don't need to do calculation. You can look at the data that you have and you can determine the answer right away. If I ask you, what will be the atomic mass of this element? So it's usually what? Near, I can say A, B, C, D. I can put here near 20, near 21, or we could say 20 to 21, 21 to 22, less than 20, or not like that, or more than 22. What could be the answer?
Option B.
A, B, C, or D?
B.
Okay. So based on the data that you have here, you will ask what is the most likely atomic mass of neon? So which is more? 20. And then 21, 22 is less than here. So most likely it's here. So those are the type of questions that you will have in your quiz. Okay. If still not clear to you, don't worry, we will work on. That's why we have this synchronous thing. So one type of questions that you will be asked during your quiz is like this one. If you're given this nuclide, you should be able to determine how many protons, neutrons, and electrons do you have. So proton, neutron, electrons. What would be the answer? We'll start with this one. So how many proton? Where will I get the proton?
Is 6 protons?
There's 6 protons. Okay. So now you have 6 protons. How will I get the number of neutrons? I'm going to use this number and then what? Subtract it with 6. So I will have 8. Everybody got that? You should, because these are the type of questions that you will be asked. Okay? Maybe the one that is given there, if the given nuclide, based on the given nuclide, which of the following is true? Okay? So you might have there are 8 electrons in the thing. There are 7 electrons in the nuclide. There are 7 neutrons in the nuclide. So it might be what we call not straightforward, but if you're given this nuclide, you should be able to know what the information that you can get from that. So how many electrons do you have? Anyone? What's the charge?
0.
It has no charge, so that means it's 0. So it has the same number as your electron. So those are the information that you can get. And the question that's going to be asked to you based on this nuclide, which of the following is true, or which of the following statements is true. Okay, and then you're given their different statements that contain some of this. That's the one that's true. So how about this one? How are we going to answer the question here? So how many protons? Okay, so you have 6. Neutron, you have 5. And since this is still a neutral charge, you have 6 electrons. So ask yourself, can you answer this type of questions in the exam?
Yes.
You're the one who will take the exam. So I just want to make sure that it is a short points on your part. Now, before I move on, how about if we have it like this? How many proton, how many neutron, and how many electron does this nuclide has? There's a charge now. You can type in the chat. So this is what? The proton is a giveaway. It's always 79. And the neutron will be what? 81. Okay. Now the electron will be based on this one. So you need a number when you add with 79 will give you plus 3. So what number would that be? When you add the proton and the electron will give you the charge. So that would be 76. Because 79p plus, okay, minus 76 will give you plus 3. Right? So question, I think I have several items on that in your quiz tomorrow. Okay. Now, atomic masses. So atomic masses, if we're going to look at it, that's just the mass of an atom in atomic mass unit. And by definition, we could say one atom of carbon 12 weighs 12 atomic mass unit. And in this scale, you will say the hydrogen is 1.008 atomic mass unit, and the oxygen 16, that's 16.00 atomic mass unit. Okay, so here we still use the so-called atomic mass unit. So this is for each atom that we have. So when we're talking about C12, that's an atom that has 6 proton and 6 neutron. Now, if it's C13, so that's an atom that has 6 proton and 7 neutron for C13. Okay, so how do we get the average atomic mass? So for instance, we have this boron. They have found to have what? 2 isotopes. So each of these isotopes has its atomic mass or isotopic mass and the fractional abundance. So the question now, what is the possible atomic mass of boron? What is the average atomic mass of boron? And I can put here, let's say, less than more than 11, less than 10. I could say between 10 to 1050, or I could put here D. So what is your answer without the calculation? We will do the calculation, but I just want you to know that you can make an estimate by just looking at the abundance. Which is present in greater amount, B10 or B11? How are you going to put the relationship here? What would I do here? Like this, like this, like this. I could put there as ABC also. So what's the relationship in terms of, we could say, isotope B10 and B11? So as you're going to look at here, this is greater abundance than that one. So we could say there are more B11 isotopes than B10. So that means between these 4 choices here, what's the answer that you can get? A, B, C, or D? You can type. So since you have 80% of B11, okay, compared to 20% of B10, I would say the choices here would be most likely this one in this range. So those are the type of questions that you ask. Now, if we're going to calculate it, how are we going to calculate it? So if you're going to look at this at the relative atomic mass, it's just the summation of isotopic mass times the abundance. So if I'm going to look at it, this will just be what? 10.013 times 0.1978 plus 11.009 times 0.0. 0.8022. What do you get? I think it's around 10.8119, or we can round it up to 10 point, and that's the one that you have there. You don't need to calculate. Okay, but if you need to calculate, this is the calculation that you're going to do. Analyze. I want you to analyze. I just do something. Question. Do you think you can get the questions like this in the chapter quiz? Here's another one. Without doing the calculation, what would be the guess? Please post your answer in the chat. So what would be the answer? Okay. So two of you answer what we call B. So let's see. So if you're going to look at this, it's between 35 and 37. And there's more of 35 compared to 37. So most likely, it's a choice between these two. But this is what you have, right? 35, 37, right? And you can see here, 3:1. What do I say 3:1? 75% compared to 25%. So your isotope 35 is 3 times more than isotope 37. So if it's 1:1, it is been between what? 35 and 36. But you have 3 more times of this, so most likely it will move towards the 35. Now, for you to determine it by looking at the calculation, you can use it like this. There's a calculation basis for this one. Now, you know why I did this 0.7578? Because that's the equivalent of the percentage. And if we have it, you will end up with 35.45. So you think you're going to get correct here in questions like this? Huh? How about this one? So in addition to getting the atomic weight, you also has to name the element. So all you need to do is just follow what you did, okay? So you get the corresponding contributions to this one. So this will become 0.0148. This will become 0.2360. This will become 0.22.226. And if you're going to get all of them, 203.973 times 0.0148 plus 205.9745 times 0.236 plus 206.9759 times 0.226 plus 207.9766 times 0.523. So I get around 207.18. So if you have a periodic table, you can look at it. And the one that is close to this one, 207.18 is, anyone? What is PB? Anyone? PB is the atomic symbol of what? I don't need you to memorize the atomic symbol because you will be given a periodic table. And I think in the periodic table, the name and the chemical symbol is given, the atomic symbol. So you don't need to memorize it. So PB is lead. Okay? So question, before we go to the periodic table and then the naming. But if you're going to listen to what I'm going to say, okay, you will be more prepared for your quiz. How do I get the 27.8? I did this one multiply with this, and then I add them. And the overall one that I have is 207.18. But this is just too much for you. I think the number that I have there, if I'm not mistaken, 2 or 3 isotopes to get the molar mass, to get the atomic mass. Okay? Did it answer your question, Ariana? So the next thing that we're going to do is the periodic table on how it came into being. Although we have a chapter of it in chapter 7 about the periodic table. Okay. So if we're going to look at the present periodic table, it is based on what we call Dmitry Mendeleev's arrangement of elements. So in 1869, he discovered that if the known elements were arranged in order of atomic number, they could be placed in horizontal rows such that the elements in a vertical column had similar properties. Okay, so he just based it on the so-called periodic law. So when you say periodic law, if you look at the periodic table, the properties are repeating, just like the season that we have. So it's already summer right now, and I don't know if you're in New York City, you can see how hot it is. starting yesterday. Okay, so you have periodic season, right? As the song said, winter, spring, summer, or fall. So the same thing in the elements. The properties of the elements are repeating periodically. So that's the periodic law. Okay, but the arrangement that they have here is based on, if you follow Dmitry Mendeleev, okay, it's not really based on atomic number, it's based on atomic mass. Okay, it was later arranged based on atomic what we call mass by Henry Moseley. But if we're going to give credits to what is to who is due, it is Mendeleev. Okay, so the periodic table, this is just a tabular arrangement of elements in rows and columns, highlighting the regular repetition of the properties. That's why it's called periodic. The regular repetition of properties of the elements. Okay, so this is the crude periodic table by Mendeleev. And as you're going to look at here, okay, some of them during that time, some of the elements are not existing. And it's not only Mendeleev who worked on the periodic table. In fact, there's another guy from Germany by the name of Lothar Meyer, who is also working on the periodic table. Now, the question is, why did they give the credit to Mendeleev? Meyer also arranged the periodic table in terms of increasing atomic mass. But Mendeleev got the credit because he was able to predict the properties of the elements that during that time was not yet discovered. Okay, so this element is gallium and germanium. He called it the eka-silicon and eka-aluminum. And he predicted that they exist with these properties. We just didn't discover them yet. And when they were discovered, their properties is very similar as those predicted by Mendeleev. Okay. Oh, gallium and germanium. Okay. The eka-silicon, eka-aluminum thing. So that's why Mendeleev, the Russian guy, got the credit compared to the German guy. But we will deal most of the periodic table in the chapter that is allotted to this one. Now, in the periodic table, what do we have? Okay, we have the periods and the groups. A period is consists of the element in one's horizontal row in the periodic table, while a group consists of the elements in any one of the columns. Okay, so the period is the one, first period, second period, third period. The group is group 1, group 2, group 3, group 4, and so on. And if we're going to look at the groups that we have, there are 8 A groups and the B groups. Okay, so just to go ahead to tell you that these are the period, the 1, 2, 3, 4, and these are the group elements. Okay, now as we say here, there are what? 8 A group. So these are the 8. 1, 2, 3, 4, 5, 6, 7, 8. You'll be given the periodic table in your pieces, so you don't need to worry about that. And if you're going to look at the A, this is what we call A group. This is your representative elements. And then this one is your transition elements. These are the so-called B groups. So that's the A, and this is what we call the B groups. And the 2 rows of what we call elements that we have here, this is your inner transition elements. So what they said, in each of the group, they have the same property. That's why you have a repetition of property. Okay, so each of this group, we could say alkaline metal was the first group, alkaline earth, the boron, the carbon, the nitrogen, the chalcogens, the halogens, and the noble gases. So in addition to the 8 groups that we have, as we said here, that we have these transition metals. And we can also differentiate this, what we call periodic table. You have the metals, the non-metals, and the metalloids. Now, this is very important, especially when you go to the naming. Okay, so you have here the metals. So this is the one that you have. These are the metals, and they have these different properties. And now this is the non-metals, and they have these properties. And the one in between the metal and the non-metals, we can call it metalloid, but in some group they call it as semi-metal. And they can have the characteristics of both metals and non-metals. Now you need to know what is the metal and the non-metal, because that will be the basis of naming them. Or in your chapter 9, chapter 8, chapter 8 and 9, whether you have what we call the, forget the name, ionic compounds and covalent compounds. Okay? You don't need to memorize them because you have the periodic table. This course is not about memorization. In fact, I only have one naming questions that we have. Okay? So let's look now at the so-called chemical formula. So we have these atomic symbols, right? So in the chemical formulas, what happened is, this is the mixing of atomic symbol with subscripts. So whether you have a molecular substance or an ionic substance. So when you have a molecular formula of a given substance, this is just a notation using the atomic symbol with subscripts to convey the relative proportions of atoms in the different elements in a substance. Like this one. So this is a compound that is made up of what? Aluminum and oxygen. So what does it tell us? That in a given substance there, or in a given compound, there is a ratio of 2 aluminum atom with 3 oxygen atom. Everybody got that? Okay. So we go with the molecular substance. So molecular substance is based on a molecule. What's the simplest molecule? Anyone? The simplest molecule that we have? Water. Water is made up of 2 hydrogen atoms and 1 oxygen atom. So a molecule is a definite group of atoms that are chemically bonded together. Molecular substance is a substance that is composed of molecules, all of which are alike. A molecular formula gives the exact number of atoms in the element in a molecule. So this is a molecular formula. And this is a molecule. Okay? And if you have a structural formula, it shows how the atoms are arranged to one another in a given molecule. So if we're going to look at them, so this is the molecular formula, this is the structural formula, and this is the different way that you can show, okay, the different model that you can show how the elements are arranged in a given molecule, or how the atoms are arranged in a given molecule. So if you have it like this, Now, how is the molecular substances different from ionic substances? Okay. Ionic substances are composed of ions. Molecular substances are composed of molecules. Okay. Now, what is an ion? An ion is an electrically charged particle. And how do they become charged? When there is electron transfer. Okay. An example of an ionic substance is sodium chloride. Sodium chloride is made up of Na plus and Cl minus. So what happened? Which do you think gives its electron and which do you think accept the electron? Okay. You will know that by the end of the day. So when you have an ionic substance, you could say when an atom picks up an extra electron, it becomes negatively charged. That's your ion. And an atom that loses electron becomes a positively charged. That's a cation. And when you have the cation and the anion, okay, a positive and a negative charge opposite attracts, you have an ionic compound. So an ionic compound is made up of a cations and an anions. So let's look at the difference between the two. So this is what an ionic compounds do. So when you have sodium, what happened? When it gives off its electron, it becomes Na plus. You lose the negative charge, it becomes positive. Did that make sense? Now that electron that was lost, it will be picked up by another atom. Once it picked up, it becomes negatively charged and you become the anion. And if you combine the two, okay, you have an Na plus reacting with an F minus. Here you produce NaF, and that is an ionic compound. How can we differentiate ionic compound from molecular substance? This is made up of what? A metal and a non-metal. Analyze. So when we look at these so-called ionic substances, the chemical formula of this is just the simplest whole number ratio of the different ions in a given substance. So the formula unit of the substance is the group of atoms or ions explicitly symbolized by its formula. Okay. Now, molecular and ionic substances, if we're going to what we could name the simple compounds, we can name it either what, organic or inorganic, but we're going to what we could focus on maybe the inorganic one. Because the organic is just for compounds that contains hydrogen, oxygen, okay, or carbon that combines with hydrogen, oxygen, or nitrogen. You cannot say organic is mostly on carbon because CO2 or CO is not an organic compound, but it contains carbon. Okay. So the organic compounds that we have here, we're not going to name it, but when you go to Orgo, you will have the naming there. Now the ionic compound, as I have told you, they contain a metal and a non-metal atom. For the molecular substances, most of them contains only a non-metal with another non-metal. Okay. Now, how do you name an ionic compound? So you need a periodic table. Why? Because the group number will tells you what will be the charge that they form. So if you have a group, what we call the periodic table, I'm going to go back to the periodic table that we have here because I'm going to break with the PowerPoint that we have here. Just want to make sure. Although if I'm not mistaken, maybe the best way I would have is I have another slide for the naming. Here, I think with regards to naming, we will go on this slide. So as I told you, the periodic table is very important for you to guide. But as I have mentioned you, I didn't focus more on this one because I don't want my students to memorize only. Okay, but I'm still going to show you how to do the name. I only have one question there about naming. So in the naming, you need to know the periodic table. So as I told you, metals and the non-metals. So we focus on the representative elements because transition metals is a little bit complex. Why? Most of the transition metal, they have more than one charge. At least in the representative element, group 1 will always have +1, group 2 will always have +2, group 3 will always have +3, and then when you get 4, 5, 6, 7, 8, so this becomes a little bit different from this one, especially if you have 6 and 7. So if you have group 6, you just subtract it with 8, giving you -2. Why? Because these are non-metals. Non-metals, they form a negative charge. Metals, they form positive charge. Okay, metals, cations, non-metals, anions. Group 7A, 7 minus 8 will give you -1. 5A, some of them, +5, some of them, -3. Okay, whether they're metal or non-metal, and as you can see, there are some semi-metals in this group. So how do we do the naming? Okay, so this is the one that I use in the naming nomenclature. So the first thing that you're going to ask yourself, what type of compounds do we have? So we already discussed ionic compound. Now, we didn't discuss covalent compound per se, but that's your molecular substance. Okay. The acid is a special case. These are just any element plus H or any polyatomic ion plus H. Now, we go with the ionic compound because that's where we left from our main lecture. Ionic compound, as I mentioned, you look at the periodic table, if there's a metal and a non-metal, that's an ionic compound. Okay, composed of cations and anions. Now, some of them we could just say binary. What is binary compounds? Anyone? Hello? What do you know by the name binary? Binary is the means they're just two elements that you have done. So as you're going to look at this, Ionic compound, cations and anions. So if you have binary compounds, it's a metals and a non-metals. Now you have some sort of these polyatomic ions or polyatomic anions. Polyatomic cations or polyatomic anions. What are these? They contain more than one element, and usually they have a charge. So if it's a positive charge, you have a polyatomic cations. If it's a negative charge, polyatomic anion. So the type 1 that you have, only one type of cation is observed. In the type 2, more than one type of cation is observed. What does this mean? These are the one that is in the transition element. Okay. This one, whatever the charge, that's the only charge that you have. This one they can have more than one. Now, if it's a covalent compound, it's made up of what? Non-metals and another non-metals like H2O. That's a covalent compound. That's a molecular substance. Now, the acid, as I told you, it's one that has an H binded with another element. That's an anion. That's your binary acid. And it contains an oxygen and another element in your anion. That's your Oxy Acid. Okay. So what's the rules for naming the ionic compound? So the first thing for you to do, the first rule is you have to know that it is ionic, because there's a different rule in ionic compound and there's a different rule in covalent compound. So how do you know? It contains a metal or it has a positive charge or a negative charge. It's a polyatomic ions. That's why I don't want to you to concentrate on this for the exam, because it will be, you have to memorize a lot of stuff. So I hate memorization. I want my students to understand. Okay. Chemistry is not memorization, it's more on analysis. Okay. So you determine whatever you have there. So what's the cation? And then the next thing that you're going to do is your cation a type 1 or a type 2. So a type 1 cation are the A group. A type 2 cations are the B group. Okay. Why did I say a B group? Let's say gold. Gold can have Au plus or Au3 plus. So the cation is first name and the anion is named second. So if we have, let's say the one that we have here, magnesium F2. So the cation here is magnesium and the anion here would be the F, which is the fluorine. So this is a combination of these. Now the anion, what they do is they just take the root name and they add the suffix IDE. So this now become like this one. Now, as mentioned here, you have polyatomic cations and polyatomic anions. You have to memorize, but I'm not going to ask you. Maybe normal semester, yes, but summer, I told you, I'm a little bit lenient. Okay, so if you have a polyatomic ions, they are made up of 2 or more elements forming a charged ion. So these are just some of them. So the perchlorate, chlorate, chloride, hypochlorite. Okay, or if we're going to look at this, we have here the nitrate and the nitrite. But I'm not going to ask you to memorize them. I make sure that I'm not going to include them. Okay, because I don't want you to waste your time here. And there's only what, one question? Okay. Now, For those type 2 compounds, although you said we said that can have more than one charge, you can determine the charge based on the given anion. So for instance here, how did we know one is FeO and the other one is Fe2O3? So the way that we're going to name this is what? Iron 2 oxide. And this one is iron 3 oxide. So the Roman numeral number here tells you the charge of that iron. So what tells us that this is a +2 and this is a +3. So usually you look at the anion. Oxygen has only what? A charge of -2. So a +2 plus -2 will give you 0. So FeO has a charge of 0. Now on the other hand, this one, Fe3 plus, you multiply it by 2, you have a +6. Now, as I've told you, oxygen will always have what? 2 minus. So you can put this as -2 times 3 will give you -6. So you can always write this as F2O3. Now, what if I ask you, write the formula of iron 2 chloride? How are you going to write it? Or write the formula of iron 3 chloride? Anyone? Because these are the type of questions that I ask, but I only put one question. If you're still there, can you write the formula for these two? Iron chloride. Anyone? So this is what? Fe Cl2 and the other one is Fe Cl3. Or the old name that you have there, the lower one is OUS and the other one is IC. So the other one we could say is a ferrous chloride and the other one is the ferric chloride. But to simplify the thing, we just have the Roman numeral number. But you only use that for elements or cations that is more than charge. You cannot write this as what? This one, you cannot write it as magnesium 2 chloride. Because you only have one magnesium charge and that's +2. Okay, so you cannot write it like that. Okay, so these are the other type 2 compounds that you can use. So as you could see there, the lower charge is OUS, the higher charge is IC. So the unique question is this one. Or Horus and Auric. I don't know if you watch James Bond. There's a guy named Auric Goldfinger. So his first name is Gold. His last name still contains gold. And the story is about gold. Okay? So now, the way that you name the covalent, no, not covalent, the ionic compound is cation and then an ion. So let's try. If you're not going to what we call the answer, then we just go with this because maybe when I told you I'm not going to concentrate it for you to think that I'm not going to do this. But remember, in the succeeding chapters, you need to know how to write the formula if you're given the name. It doesn't mean that it's not part of the quiz. You're not going to study on this anymore. Okay? So let's try to what we call do some naming. How do you name this one? Anyone? You can type your answer in the chat. Okay. So this is sodium oxide. So most of you are not participating anymore, but I can't blame you. Okay, so how is the covalent compounds different from what we call ionic compound? Now, in the covalent compound, they're made up of what? Non-metals. Okay, so if they're made up of non-metals, that means you're not going to name them similar to ionic compounds, which made up of metals and the non-metals. So the main difference of this, what we call covalent compounds, is the use of the so-called prefixes. Okay, so the use of prefixes denotes the number of atoms present in a given compound. So that's why if you're going to name this CO versus CO2, what do you name them? This one is, if you follow the rule, monocarbon monoxide. And this one is monocarbon dioxide. But they simplify the naming. If the first element is only one, you can drop the prefix mono. You only use the word mono in the second element. And just like the ionic compound rule, you also use the so-called suffix. You convert whatever last name, the name that the element is to IDE. So you have your mono and dio, and then you have site. Okay, so how do you name this one? N2O5. Anyone? How do you name N2O5? Anyone? So N25 is dinitrogen pentaoxide. Now, the last one that we have here is the acid. So if ever you have this covalent compound, these are the prefixes that you have. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. So the way that we have the convention, prefix of the non-metal plus the prefix of the non-metal root and IDE. But if this is what we call mono, you can drop away the word mono. So anyone, what do you have here? P4O6. How are you going to write P4O6? Anyone? Okay, the first one to answer, I give +1 in the first chapter quiz. Because it seems to me that you're not what we call participating. But you can only get +1 for the session. Is it tetraphosphorus hexoxide? Try to look again. How are you going to write a name P4O6? Okay, anyone? So no one wants to bite it. So it's tetra phosphorus hexaoxide. So make sure two words. You put the prefix together with the name of the element. Okay. So how about if you have it like this? How are you going to name ClO5? So you have one chlorine there and 5 oxygen. So you can have there chlorine. That's 5 pentaoxide. So that's how you name the binary covalent compound. Now, the last one that we have are the acids. How do we determine if something is an acid? Well, it's always what we call the presence of H plus. And if we have here the presence of H plus, what does it mean? Okay, so anything that has an H plus another element, that's an acid, and that's a binary acid. And anything that you have, let's say an X and an O, okay, that is an oxy acid. Now, usually in the oxy acid, the number of the oxygen varies. Okay. Now, how do we name an acid? So when we said HCl, do we name it as hydrogen chloride? Do we name it like this? The answer is no. When you have an HCl, okay, you don't name HCl as hydrogen chloride because it is an acid. So when you have what we call an HCl, you name it as, put the word hydro and then the root word and then add an IC. So you have here an hydrochloric acid. Okay, so the convention that we have for binary acid, we have the word hydro and then the non-metal root word with the IC plus the acid. So if we have it like this, how do we name it? So we have what? Hydro. What is Se? Selenium. Okay. So we have here selen, because we're going to replace the last word there with IC. So we end up with a hydroselenic acid. Okay. So we don't name this as hydrogen selenide. Okay. Once we have an H, it's automatically an acid. So that is the rule for binary acid. So these are the example that we have: hydrofluoric, HF, hydrochloric, hydrobromic, or we can also have the one that is the what we call oxy acid. Okay, so as a whole, they have here boric acid, carbonic acid, salicylic acid. But if we're going to look at this, there's a way to name them. Okay, so depending what's the name of the ion, okay, there's a name that corresponds to them. So what do you see? Anyone that ends with ITE becomes an OUS, and anyone that ends with ATE becomes an IC. So see this one? All you need to do is what? Replace this and add the word acid, hypochlorous acid. chlorous acid, chloric acid, perchloric acid. So if you have, let's say, NO2 and HNO3, so this one is what? Nitrous acid, and this is nitric acid. So that's the main difference. So try naming the acids formed by nitrite and the nitrate. So that's just the nitrous acid and the nitric acid. So that's what we have in the naming. Okay? And as told you, to simplify the thing, I only include one questions on that because I don't want you to concentrate on that thing. Okay? But we're still not done with our lecture, because what we're going to do once we're done, maybe we can look at some of our problem set. I think some of you have noticed some of the questions that came out is in your what we call problem set. So we're done already here. So the next thing that we're going to do after the naming this one, writing chemical equation. So what do we have here now? So we build up the element into compounds. We build up the atoms into molecules, the atoms into ionic compounds. So what we're going to do now is maybe we can react the element. So in every reaction, it's always represented by a chemical equation. Okay. So for instance, if you have the burning of sodium and chlorine to produce sodium chloride, so the reaction that you have here is you have two sodium atom reacting with a chlorine molecule to give you 2 sodium chloride. So what do you see here in your what we call chemical equation? You see here the so-called reactant. So when we say reactant, that's the starting materials. And you also see here a product. And in addition to that, you see the physical states of the species in the reaction. Now, another thing that you're going to see here, if you write a chemical equation, okay? So as I told you, reactants are starting substances, and then the products are the one on the right side. So if you're going to look at this, okay, you also like to put there the physical states. And as much as possible, you want the reaction to be what we call balanced. What's the basis of that? So if I have a question in the quiz, why is the chemical equation needs to balance? What law needs to be observed? What law is that? Anyone? What law? What natural law could be the basis for this what we call balanced chemical equation? So it has something to do with the law of conservation of mass. So how are you going to write the law of conservation of mass? So to follow the law of conservation of mass, you just need to make sure that the number of the elements in both sides are the same. So that's the way to say you have a balanced chemical equation. Okay? So is this balanced? Is the given equation balanced? So if you're going to look at this is not balanced. Why? CHO. So if you're going to look, C is one here, here, 1. Hydrogen here is what? 4. Here, 2. Oxygen is 2. Here, oxygen is 2. Here, 3. So we need to balance it. So how are we going to balance it? This is the methane combustion to produce carbon dioxide and water. So how are we going to balance it? We balance it by trial and error. Okay? Usually you start with the more complicated and then go to the simpler one. So which is not balanced? Hydrogen and oxygen. So in doing that, what will happen is the hydrogen that you have here is 4, this one is 2. So as you could see here, oh, if I put the 2 here, so this becomes now what? 4. And in addition to that, your oxygens now becomes what? 4. So I balance already the hydrogen, and all I need to do now is balance the oxygen here. So I have 4 oxygen here and 2 here. So I put the 2 here. So I already have a balanced equation. And a balanced chemical equation should be what? In its simplest, whole number ratio. So what's the number that we have here? Automatically, if it's 1, you don't need to write the number 1. Okay? So let's try this one. So remember, in balancing equation, the only one that we change is the coefficient. We don't change the number of atoms of each element. We don't change the subscript. We only change the coefficient, just the number in front of them. So how are we going to answer this one? I think I did a step-by-step here. So you have what? C2H6O. Okay. So that's the step-by-step. But the way I do it is I line up every element and then put reactant and product. And then what do I do? Count here 2. Hydrogen, there is 6. And then oxygen here is 2. And then you have your carbon as what? 1. Oxygen 2. No, not 2. 2 plus 1 there, that's 3. And the hydrogen I have here is 2. So which one do I need to balance first? I go with the complicated one, the more complicated one. So in this case, I would say I'll put a 3 here. Okay. And if I put a 3 there, what will happen to my hydrogen? It becomes 6, and my oxygen here will become 3 times 1. So that's 3 plus 2 here. That becomes 5. Now what else I need to balance? The oxygen here. I mean the carbon. I need 2 here because I have 2 there. So in doing that, so I have what? 2 times 2, that's 4, plus 3, that becomes 7. Now you may ask yourself, I have 7 oxygen here and I have 2 here. Can I just make it like this? The answer is no. Okay, so what you need to do, if it's 7 over 2 here, you multiply everything by 2. So this becomes 2, this becomes 7, this becomes 4, and this becomes 6. And all you need to do is to check if the number of the elements on both sides are the same. So you have here 4 carbons, 2 times 6, that's 12. And then oxygen is 14. And then on this side, 4. And then the hydrogen here is 6 times 2, that's 12. And then you have 4 times 2, that's 8. Times, no, not times, plus 6, giving you 14. I think I did it already here at the end. So this is the elements that you have. This is the balanced chemical equation. So if you want to check, this is what we did initially. Question.
Yeah. Yes.
So question. Anyone who wants any question? Don't be shy, because I want my students, at least if ever you didn't do well, you end up maybe with a C. But as much as possible, some students cannot do that. Okay, I never have a students who failed during the summer, but that doesn't mean you don't going to do your part. Okay, because if you do your part both in the lecture and the lab, I think you will be fine. So any question? I'm opening now the time for questioning. Are you okay with the setup that we have? Anyone? Because as I've told you, I want you to look at to watch ahead the video that I have from the fall semester, and I'm hoping that during this time there will be more interaction or questions, more on clarification. I'm still willing to repeat it, but the thing is, because I try to condense everything in a shorter time, unlike the one in a typical semester. So this is most likely like a package deal that you do that part here, and then we do additional problem here that you have. So what do you think we can utilize this time now? We still have more than 1 hour. Don't worry about your results, okay? Because the way that I'm going to do this is arsenic. How do you name this? So this is an arsenic selenite. This is an arsenic oxide. This is a sulfur dioxide. This is a tetraphosphorus hexaoxide. And this is a dinitrogen monoxide. Okay? So ASO 23223. Nope, that's 5. And sulfur here is 1. So how am I going to what we call change this thing? So maybe we go with the sulfur. The sulfur is what? 3 here, so I can start with a 3. But my oxygen becomes 3 times 2 there, that becomes 6. Plus 3, that becomes 9. And then what happened? I have here 2 oxygen, so if I'm not mistaken, 9. So I can just put a 9 over 2 to give me 9. But as I told you, you cannot have a fraction. So I just put this one because what you're going to do, you multiply everything by 2 here. So this is the one. That is a balance equation. Okay. Now the last one that I have here in the balancing is this one. calcium phosphate plus phosphoric acid to produce calcium hydrophosphate. So CpOH. So how many calcium here? 3. Phosphorus, 1 times 2 plus 1, 3. Oxygen, 4 times 2, that's 8, plus 4, 12. And hydrogen is 3. And then you have 1, 2 times 2, that's 4. 1 times 2, that's 2. And 4 times 2, that's 8. So what do we do? As you could see here, calcium is 3 here, so I can put the 3 here. You always go with the complicated one. Now, once you make it 3, everything changes, right? So what will happen here? Your hydrogen now will become 2. Whatever you have here, it's all 3. So this is 8, 6. So 8 times 3, that would be 24. And hydrogen there, 2 times 2, that's 4, times 3 will give you 12. So what will happen? Maybe you can multiply here with a number. So hydrogen, that's 3, and then 12. What's number? When you multiply with 3 will give you 12. So 4. So this becomes 12. And the oxygen here, 4 times 4, 16, plus 8, that's 24. And then phosphorus there, 4 times 4, plus 2 there, that's 6. So that's what you have. Okay, so before I end this one, I just want to have some what we call nuclide answer question, and I want you to answer on that, just to prepare to you in the exam. So how are you going to put this? How many protons, neutrons, and electrons does this have?
9 protons.
9 proton. And then
11 neutrons.
11 neutron. Okay.
And 1 electron.
So how many electrons do we have?
1.
Is it 9? So as you could see, the net charge is -1. So that means it's just like 9 minus 10 will give you what? -1. Analyze, because I want you to have to get the correct answer for questions like that. So let's go with another one. So how are you going to answer that? Sodium plus. Sodium 24 plus. Anyone? So 11 proton. How many neutron? $13. And how many electron? Anyone? 10. Because 11 11 minus 10 will give you plus 1. So question. Don't be shy. You're paying me to do this, to answer question. Are you ready for the chapter 2 quiz? Question? So do you have any question, class?